Welcome to our talk. Hope you're having a good conference so far. This talk is about event-driven data science. So it's a bit of um, a meta talk about how you do data science. This is us. I'm Patrick Deziel. I'm a distributed systems engineer, machine learning specialist. That's kind of a long job title, but I'm also a Python Go programmer, and I also enjoy rock climbing. I'm joined by my coworker Prima Roman. She is also a distributed systems engineer, ML ops specialist, and she does teaching at Georgetown University and enjoys walking around DC. So she'll be showing a bit of a more practical demo later on in the talk. But first, I want to start with the question of why is it so hard to get models into production? So I'll start with this quote, which is 87% of data science projects never actually make it into production. And I think there's a few ways to actually interpret that. One is that it is kind of hard for data scientists to deploy models into production. Another explanation might be that most data science projects actually just fail. Um, so there are a few things to think about as we go through the rest of this talk here, but I want to start with something called the Kaggle effect, which is, if you know about Kaggle, it's a resource and community for data sets and collaboration data scientists. And I think what it shows is that data scientists are really good at working with data sets that are nice and bounded, and they don't have any real-time components to them. And you can train a model which works as you expect it to because you have this kind of bounded data set. And there are no really surprises once you've dealt with all the outliers and stuff. So um, if you think about what you do as a data scientist, traditionally in this batch data science flow, is that you start by ingesting a lot of data and then wrangling it and getting into the format that you want. And eventually you'll build models and maybe have some nice visuals. Uh, but the problem here is that it's basically completely neglecting the idea of ML ops. Like, how do you get these models deployed into production? Because if it's not in production, then these models are not going to be very useful or at all. So what happens is that batch machine learning, you have to have a batch of data to train a model. And then once you have more data, you have to create an even larger batch, which increases the time that it takes to train your models. So it's also increasing the time it takes for you to iterate and try new things, even though the more data is supposed to lead to better performance for your model. And the fact is that once you train the model, it's frozen to that at that point of time, so that you won't be able to actually change any aspects of that model, and it can't really react to like real-time things that are going on with like users on your system, giving you feedback, stuff like that. So let's return to the question, why is it hard to deploy? Well, one reason is you might not have enough data that you can sufficiently represent reality and what's going on in the real world. So your models might just not work out of the box, and your models might be outdated by the time they get deployed because things in the real world change very quickly, and your models will not be able to keep pace with the changing data because they were trained with certain assumptions in the past. And iteration is really, for deploying new models, is really expensive, mostly because as data scientists, we're not really trained how to do ML ops. And so if you're a data scientist, you really want to be focusing on the ML, you want to be focusing on doing the data science, and that's really the fun part. And ML ops is mostly not the fun part. So I think sometimes data science struggle to like adapt to that situation where you need to be deploying new models. So here we're going to introduce this concept of asynchronous data science, which, in contrast to this batch way of doing things, the batch way is completely linear. So you have to do ingestion before you do data wrangling and data analysis. And also every time you get new data, you have to repeat those steps over again. Which can take a long time, depending on how big your data set actually is. And you can also run into memory issues if you're just trying to train things locally or even in the cloud. So, but in async data science, you are reorganizing your data into streams, right? So you no longer have these giant batches of data. Instead, we have is like streams. And you can think of them as like topics in PubSub, right? So you're publishing and subscribing to data streams. And this means that all your processes can happen concurrently, right? Because you don't need to wait for everything, because all this is happening asynchronously. So if we look at an example here, let's say I have a recommendations app called Kelp. I guess that's for restaurant recommendations for vegetarians, I suppose. And I have this app, right, where I can give reviews and or I can give recommendations to users, and they give back reviews and ratings into the system. So my goal is to try to train like a model that can actually give good recommendations for users. But the problem is like this state is changing over time, right? Because users' tastes will change over time as they discover new things. So what I really want to do is I want to have this kind of asynchronous inferencing engine on the right here, um, which will allow me to actually get those models updated and actually personalize some of the models for the users. But how you actually integrate those things is, I think, not very clear traditionally. So one solution is to just make everything asynchronous with data streams. So what this means is that you have various topics where you have your raw data and your clean data and your process data. And what this allows you to do is if you have data streams, you can just publish and subscribe to those streams, and all these boxes kind of represent your different processes, whether it be like your different Jupyter notebooks or your microservices. Like you might have a service where it just focus on deploying models. You might have a service which is just showing the visualizations for how the models are doing, and you might have your actual application where you're using the models in production. So this way it kind of requires you to kind of rethink how you're structuring your data in your organization into like these data streams instead of these like data like lakes, or like these big data sources in your organization. So we talk about real-time machine learning. Like, how does that actually work? Like, how do you do this with the async data streams? Well, these models are kind of designed to learn one at a time, or one kind of mini batch at a time. So this means like the training cycle, it never ends. Like you never reach a point where like, okay, I'm done with this model. I'm never going to train it again. Instead, your model is continuously learning as new data comes in. So this is based on the assumption that you will have to update your model every time new data comes in. So it does make it less susceptible to drift, model drift in those cases, and kind of follows the inverse paradigm of the batch model, which is like now you're predicting and then you're fitting. So it's also referred to online or incremental learning. So I might hear that from other places. So if we compare batch-wise versus real-time or online learning, in batch-wise modeling, there are lots of tools which are kind of designed for this, and I think that's why most people tend to start with batch-wise machine learning, because it's easy to understand, and it's really good for certain use cases, like if you have to process like an entire network or compare different parts of your data set. But there's this lag time between the time that you receive new data and when you can actually update those models. So in contrast, the real-time machine learning is does make it easier to deploy new models because you have those data flows set up, and you're and it takes a lot less time to train the models because you're only learning one at a time. And but one downside might be that a lot of eventing tools out there like Kafka aren't really geared towards data scientists per se. They're more geared towards kind of like classical computer scientists or engineers who are dealing with microservices. So that might require you to kind of shift your mindset into more of a functional programming state. But real-time models are really best suited for things like anomaly detection and RAGs, where you want to have those personalized models for users, and various other things. So there are actually real use cases for these online models. So at this point, I will pass it over to Prima, so we can actually get into some code and some a demo we can show for some more practical things.
All right. Hello, everyone. I'll go ahead and share my screen for the remainder of the presentation. Thank you, Patrick. And so as you've seen so far, Patrick went over real-time learning and asynchronous data science, and how kind of combining the two would help you not only build but deploy your models a lot faster than traditional batch-wise machine learning models. And so I'm going to kind of talk to you about how you can implement an online learning application. So even before kind of getting into the weeds of the code itself, you want to kind of first be thinking about, like, at a high level, what your use case is, and think about the how the data will flow into the application. So you kind of think about like all of the different data sources that you're going to be ingesting from, and how the data transformations will occur at each step of the process. And at a high level, you want to think about the topics. And so topics are like tables in a relational database. It's a way to organize your data. But unlike relational databases, topics in a real-time system, allow you to act on data as soon as it appears, in the table, like, versus your traditional relational database where you might, extract data at some sort of an interval. And then along those lines, you want to think about the event handlers, which are going to be the components of your application that interact with these topics. So there are kind of three different flavors. So you have the publishers that will write data to a topic, and then you have subscribers that read data from a topic, And then you have handlers that are sort of a combination of publishers and subscribers. And so what handlers do, for example, you can have like a component that reads data from a topic, does its data transformation, has some results, and then publishes these results to another topic. And so here we want to introduce you to Ensign, which is a streaming data platform specifically designed for data scientists. And so the idea here is that you have a topic, let's say we call it my topic, and you have a publisher on the left that publishes what we call an event into this topic, which is just a piece of data related to your application. And as data scientists, you have two ways to interact with this topic. You can either, as we're going to show you now, how in a real-time fashion, where as soon as new data arrives in this topic, you can make inferences, you can learn on this data immediately, or you can also query for historical data, and there are definitely applications where you can just take read in all of the data that's in this topic and use it for analytics and other use cases. So it's very flexible for both batch-wise and streaming operations. And so here, let's actually take a look at a specific use case. So imagine you're a restaurant owner, and a lot of your customers, you want to make sure that your customers are happy with the experience at your restaurant. And so a use case would be where you can ingest data from Yelp, because oftentimes it's a very popular platform for people to publish reviews. And so you have a publisher that ingests data from Yelp, and then takes that data and publishes it in a topic called review. And then you have a subscriber on the other end that as soon as new data arrives at this review topic, it will subscribe to this data and then initially do an inference. So we talked about online learning, where you have it's a predict fit paradigm. So it'll first make the inference, and then it'll then use a label to learn from that record. And then now you have an inference and you have the label. You can use it to compute metrics, and then the subscriber can then publish this metric to a metrics topic, and then you can have another subscriber on the other end that as soon as it sees the metric, it will compare it to a predefined threshold and send an alert if a metric falls below that threshold. So now here you have an opportunity to do not only building a model and learning from the model, but you also have a way to monitor and do all of that in real time. And so now let's get to the demo portion. So the code is available here, and essentially there's three main components of this application. You have a Yelp data publisher that will do the publishing of the data, and then you have a subscriber on the end that will run the inferences and learn from the application and publish metrics to a metrics topic. And then you have a metric subscriber that will then read the metric and see if this metric is if it falls below a threshold, it will print out a message saying that the metric is below below the threshold. And so I kind of have this set up here. So these three components. So we'll first run the metric subscriber, and then we'll run the Yelp data subscriber, and then last we'll run the Yelp data publisher. So you can see kind of in real time, like as soon as data appears, you have, in the first section, you can see the data, and here you can see the precision and recall metrics for each record. And then you can see here, in the cases like where the scores were below the threshold, you can see that this is printed out. But then imagine like how in real time you can, have this kind of a notification set up so that you can react immediately. And so kind of going back to the talk, we invite you to try out real-time models, and you have two ways to do this. So the first is you can try out the Ensign sandbox, and it is, it's free to use, and we have, if you click on the Ensign U link, you have a lot of resources that you can use to kind of help you get started, and there are a lot of examples that you can play with and use the PyEnsign SDK. So it's a Python library, just like you use for interacting with Ensign. And then the other option is that we are offering 5 pro consultations, and you just have to bring your data source. And we have years of experience building machine learning models and deploying them, and so we can help you build your application. And if you're interested, you send us an email, and this offer ends this coming Monday, so you can send me an email if you're interested, and then we'll help you out. And I'll now open up the floor for questions.
Let's see. It looks like there are a few in the Q&A. So if you want to navigate over there, how would you? So first one is, how would you validate that a model update actually improves the model performance?
So there's probably a few ways to do this, because as I mentioned, like you have the precision and recall. So we had the precision and recall scores. So if you kind of want to see, like for each record, like did the score actually improve, you can you can hold the previous precision and recall metric, and if you want, you can compare the current precision recall or any other metric that you're looking at. And actually, the one thing that I didn't mention was that when you actually run that particular example, like you saw those alerts coming in, and initially, like as you would expect, when the model's first learning on this data, the scores are not going to be that great. But then you'll see that as the model continues to learn and gets more instances, it actually adapts, and over time those scores actually improved. But as at each level, you see the scores, and so you can see what the latest score is and kind of compare it to the previous scores.
Awesome. Another question is, how can we solve the latency problems? Example for an IoT scenario.
All right, Patrick, would you like to take this one?
Sure, I can take this one. That's a great question. I think the interesting thing about data streams and online learning is that I think the latency is actually probably going to be less than if you're doing the batch wise modeling, because as long as you're publishing, as soon as you get the signals from your IoT, then you should be able to be as up to date as possible. So I do think that the latency problems are kind of alleviated by the kind of data streaming methodology, but I do also see situations where you might be still having to deal with that latency. So that's a good question.
And then same individual who asked that last question, where is the checkout list?
Actually don't know what that refers to.
All right. Ali, if you could specify back in the Q&A, that would be awesome, but we'll move on. So what does eSign offer compared to other streaming frameworks?
Yeah, it's a good question. So Ensign, like there's definitely a lot of options that you have for data streaming and eventing. What Ensign is, like one difference is that as well as real-time data, you also get access to all of the historical data that you've published to any topic. So that happens by default. So in other systems, they might be more stateless or by default, so that you don't get to view the historical data and run queries on it. You would need some other tools to kind of help you with that. And also, what we really wanted to do is design the API in a way that's very Python friendly and very developer friendly. So as you saw, like earlier in the slides, like publish and subscribe should be like one-liners, and you should only need to know what data stream that or topic that you're connecting to. So ease of use and persistence would be kind of the two main differentiators that we were kind of building for.
All right. So going back to the where is the checklist? So it says you have it on your slides. Example: what real-time models are best suited for this slide? It has a checkout list, but there is not a link mentioned. Can you give us the link? So it looks like it was
okay.
on
I
one
see what
of
you're saying. Okay, so
slides.
there is a slide earlier. I don't know if you, Prima, can go to that, where we mentioned like we linked to like, yeah, that's it. One slide more. There's a link to
Was it? Yeah, let's see.
yeah, there. This one. So I wonder if I can get that posted link.
There. Okay. Let's see if we can post this. I can probably post this here. There you go.
Awesome. So we got that. Is this a local pub sub async solution orders, or does it work in a cloud distributed environment, etc.? Or example rather, Azure services.
Yeah, great question. So what the solution, the Ensign is a managed service. So and we're basically cloud native. So it's just Kubernetes. So we could deploy anywhere we want to. But what you're really doing when you're doing the publish and subscribe is that you are connecting to our broker, to our managed broker in that we're hosting. So you don't. The big advantage of that is that you don't have to host anything. You just have to have an API key. That's it.
Awesome. So with the last 120 seconds or 2 minutes, any other burning questions, please put them into Q&A. Oh, there we go. Can we have self-hosted brokers?
That is also a very good question. So all the code is open source. So if you want to, you could build it yourself and run your own broker. That's how you would do it right now.
Yeah, I just want to add that one of the advantages, of using Ensign is, it's kind of specifically for, data scientists. Like, there's a lot of work that you have to do, like just in terms of building a model and working to like deploy the model, and then having to think about DevOps is like having to like add another skill set. And we're kind of the advantage that Ensign offers is that because we are a managed server, like you don't have to worry about allocating CPUs or memory and thinking about all of those kinds of things. And that's something that we handle. And so this kind of helps you kind of focus on kind of what you do best, which is to build machine learning models.
And then one last quick question before time expires. Is this or supported for Julia language?
So it's a great question. We'd certainly like to develop more SDKs in the future. Currently, we support Python primarily and also Go. So those are the two SDKs that are available right now.
Awesome. And that will bring us to a close. Patrick and Prima, thank you greatly for this awesome presentation, and thank everyone for hopping on and taking some time out of your day to attend. Obviously, we can continue this conversation in Discord. There will be a recording if you want to play it back or share it with any of your network. But I'm going to end the session so everyone can get to their next. Again, thank you everyone for attending, and I look forward to seeing you in a session very shortly.